Okay, so good morning, everyone. So yesterday we were discussing about how multiprocessing systems or multitasking systems nowadays work, and we understood that system calls have a key role to play in the working of multitasking systems. So today we will study about system calls in more detail. Let me remind you the context in which we discussed about system calls yesterday. One was that so we understand that there can be multiple programs in the memory of a computer at a certain point of time. And at one point of time, one program will be assigned the CPU. So that is the program which is executing right now. The operating system as well as all other programs are not executing at this point. Right? So at a particular point of time, one program will execute. However, which program is executing, this we want to change over time. So we want that the CPU will be allocated to different programs at different points of time. Let's say the duration of 1 second will be divided into several small parts so that each small part is allocated to one program at a time. Now, of course, who will do this? Who will do this allocation? The operating system. Remember that the programs that you write or all other programs, they are under the illusion that they are the only program in the system. Right? So when you write your C program, think about when a lab goes on, like PDS lab or algorithms lab or anything. Possibly all of you, at least in the days when you were in maybe when we actually had to had physical labs sitting in the department at IIT Kharagpur. Probably all of you logged into the same server and you are doing programs. However, any of you could think that your program is the only one running on the system. You do not need to worry about other programs. This is because the OS is creating an illusion and it is allocating the CPU to your program intermittently. Now, of course, suppose your program is running now. At some point, the operating system has to run. That means the kernel has to run so that it can give the CPU to some other program. How will the kernel run? So there are two ways. One is that your program makes a system call, like a printf, scanf or something, because of which the kernel starts running. And then the kernel may decide, like say you have wanted to take a large amount of input. Then the kernel starts running because you have made a system call. The kernel may decide that, oh, this input will take time. Therefore, no point in keeping your program. No point in keeping your program on the CPU because your program has to wait, and we don't want CPU cycles to be wasted. So rather, start your input, maybe start the input process. Right? So we discussed that the kernel may actually talk with some device driver, etc., to start this input, and then it can allocate the CPU to some other program. So that is one mechanism, right? So your program makes a system call. The other possible mechanism we discussed is that maybe your program is not making any system call. However, after a certain interval of time, it is expected or it is desired that the CPU will be allocated to some other program because we won't allow, it is not good that only your program keeps on executing. So at that point, we decided a mechanism called a timer. So the timer is a special piece of hardware which the kernel sets before giving your program the control of the CPU. Now, when the timer will interrupt, then again the kernel will start running and it will decide which program to allocate the CPU next. Okay, so system calls play a big role in these kind of changing the CPU from one program to another. So today we will discuss system calls in detail. So again, if you have any questions, write in the chat, or at least maybe write in the chat question, then I will give you a chance to ask. Okay. So what are system calls? The mechanism used by an application program to request service from the operating system. What kind of service? Say taking input or outputting something, right? Or even accessing memory or something like that. So we have seen this picture, a representation of this last day also. Let me repeat. So we understand that the CPU functions in two modes, user mode and kernel mode. Usually when kernel code is running, then the CPU is functioning in kernel mode. And when your program is running or an application program is running, then the CPU is working in user mode. So let's say a user process is executing and that program makes a system call. So then the mode changes to kernel mode of the CPU, and some part of the kernel starts running, which will execute this system call. And when that is over, when execution of this system call is over, the mode will return to user mode and the control will again come back to the user program or the application program. Right now, as we will see that depending on the system call, the part of kernel code which will execute the system call will be different. Right, that we will see today. So in this lecture, we will talk about system calls and interrupts, because at earlier days, system calls were handled very similar to interrupts. We will discuss that. So first, because system calls were handled similar to interrupts, we will discuss about interrupts first, and then understand in earlier days how syscalls were handled similar to interrupts. Then we will also discuss that nowadays system calls are handled in a bit different way, that we will discuss. And we will also discuss examples of common system calls. So in the earlier days, system calls were issued using int instruction and were handled similar to interrupts. So in order to understand that, let us have a brief overview of how interrupts work. So usually there are two types of interrupts provided by a processor: synchronous and asynchronous. What's the difference? The synchronous is kind of, you can predict. Okay, maybe that's not a good way of representing it. In synchronous, it is kind of known that under what circumstances such an interrupt will come. So basically, such interrupts will happen every time a particular type of instruction executes with a given instructions, given program state. So let's say anytime a program divides by 0, a particular type of interrupt will occur. Or maybe a bad pointer dereference. So you see, so these are two error conditions, you might say, that divide by 0 or bad pointer dereference. So when such events happen, then a particular interrupt will occur. Or let's say the application actually wants some service, input, output, or something like that, maybe malloc, etc. So again, when such kind of instructions are executed, then it is known that whenever such instructions are executed, then a particular type of interrupt will occur. Right, so these are synchronous. It's defined that when such interrupts will occur, say synchronous interrupts. When I say it is defined when it will occur, don't think of time, because clearly the OS has no way of knowing when your program will ask for input. So it's not the question of time, knowing the time. But what I mean is that under what circumstances or under what situations such asynchronous interrupts will occur, that is well defined. The other type of interrupt is asynchronous, which can happen anytime. Like there's no way for the kernel to know when under what conditions such asynchronous interrupts will come. They are usually caused by an external event, that is, say, by some IO device. So we discussed this in a previous lecture, that let's say the kernel has started an IO operation. Now, when that IO operation completes, the IO device will inform the kernel that the IO operation has ended. This is usually done by raising an interrupt. Or say the timer, which we have discussed. So when the timer ticks, or the timer says that maybe the amount of time to be given to a process ended, so then timer, as asynchronous interrupt is raised by the timer. Now, so these are the two types of interrupts. Now, Intel gave two specific names to these two types of interrupts. The asynchronous interrupts were actually called interrupts, and they used a different term called exceptions for the synchronous interrupts. Yeah. So sometimes in books you will see these terminologies also, exceptions and interrupts. However, from the programmer's perspectives, you can think that these two types of interrupts will be handled using the same abstractions. Like more or less, whenever these happen, maybe the program which is running will be saved, the context will be saved, and then some part of the kernel will run to handle the interrupt and so on. So those things kind of remain the same. Though again, we will come to this. The part of the kernel which runs depends on what type of interrupt has been raised. We will come to that soon. So each interrupt or exception includes a number indicating its type. For example, 14 is a page fault. What is a page fault? We will discuss this in a lot of detail at a later part of the course. Just for now, just one line explanation. Suppose actually the memory of a computer is divided into parts called pages. So suppose a program asks for some data which is currently not in memory. So it is in disk, it has to be fetched to memory before giving the data to the program. Then a page fault occurs. So basically a program has requested for some data which is not currently in the main memory. So that is a page fault. But again, we will discuss this in a lot more detail later in the course. So let's say when a page fault occurs, interrupt number 14 occurs. Now the kernel has to know that when a particular interrupt occurs, which part of the kernel to execute, which function, let's say which function or which module to execute when a particular interrupt occurs. How will that be decided? So kernel creates an array of interrupt descriptors in memory called the interrupt descriptor table or IDT. So the number is indexed into the IDT. So essentially, say in the 14th location of the IDT, say in index 14 of the IDT, it is noted the starting address of that instruction which will start servicing this interrupt. Okay, so let me repeat. There is this table called interrupt descriptor table, and the interrupt number is an index into the table. The entries in that table contain let's say the starting address of that routine of that function which will handle this interrupt. Now this IDT can be somewhere in the memory. The starting address of the IDT is pointed to by a special register called IDTR. And each IDT entry J, that is for the interrupt number J, specifies things like what code to execute for interrupt J. It's also called the interrupt handler, this part of code. So the code which will handle interrupt J is called the interrupt handler for J. So the IDT entry J specifies things like the starting address of that code, which code to execute for interrupt J. Again, the privilege level necessary to raise the interrupt. So for example, a user program cannot raise the interrupt for page fault. Usually the user program will just ask for the data. Again, some part of the kernel will understand that data is not in memory currently. So then that part of the kernel will generate a page fault. Okay, but essentially, so somewhere, so I hope you understand this part, that from your core knowledge, that basically there are things like program counter, right? So ultimately the address of the next instruction to be executed should be loaded into the program counter. So suppose interrupt number 14 has occurred. What is the next instruction that the CPU should execute? The next instruction should be the first instruction of the interrupt handler for interrupt 14. How to find that instruction? That is what we are discussing. So there is a table called IDTR, and it is known that the 14th location of that IDTR will help to identify the address of the next instruction, which should be executed for servicing interrupt 14. Okay. So this is like a picture, pictorial view of what we were discussing. So there is this big table, and each entry contains information about a particular interrupt. And the starting address of the table is held in a register called IDTR. So if interrupt, say 47 occurs, the CPU knows that it has to go to this table and look up index 47. And that entry will tell what is the next instruction to be executed, so that the interrupt handling routine for this particular interrupt starts running. Now, we discussed this, if you remember, I think yesterday or even before that there are different types of interrupts. At least the two broad types are hardware interrupt and software interrupts. So things like, say, page fault, that is a hardware interrupt because it's got to do with something in the memory. Also, there is a software interrupt. So the program can actually raise an interrupt. And for that, there is this instruction called the int. So int, and then you specify a number. This instruction allows the software to raise an interrupt. So what happens if a program issues int, say num? Again, the same thing. Control jumps to the kernel at a prescribed address. That is the address of that interrupt handler for this particular interrupt. And how will the kernel find that, or how will that address of the interrupt handler be loaded into the program counter? That is by this mechanism which we discussed. So the address of the interrupt handler will be found using the IDT, and that interrupt handler will start running. However, before that, we discussed this, that the state of the program which was running till now needs to be saved, because at some later point of time this program will have to be resumed again, right? So therefore the register, so before starting to run the interrupt handler, or maybe right at the beginning of starting to run the interrupt handler, the register state of the program is saved by the kernel. Okay. So we'll just come to this point in a bit more detail. So the register state of the program is saved by the kernel. And so then the interrupt handler starts running. It handles the interrupt. And when that is completed, handling the interrupt, then resume program. So because we know that we have to resume the program, we do this. The register state of the program is saved by the kernel. Okay. Now let us understand this point a bit more in a bit more detail. How can the state of a program be saved? Essentially, if you think, okay, I see a question. Should the program be running in privileged mode? Which program? Can you unmute yourself, Simant?
Hello.
Yes.
So the program which raises the interrupt, shouldn't that be running in a privileged mode? Because on the previous slide you just mentioned that interrupts can be raised only in the privileged mode.
What? Sorry? Oh, what did you say about privileged mode?
Sir, here, last line, privilege level necessary to raise the interrupt.
So
User program cannot raise interrupt.
yeah, there are some specific interrupts which cannot be raised by a program running in user mode, but not all. Specifically, this line says that the interrupt for page fault, right?
Oh,
That's
okay.
interrupt number 14, that cannot be raised by a user program.
Okay.
But clearly, user programs can raise, there are lots of interrupts which can be raised by a user program also.
Okay.
That is what we are discussing here by the software interrupts. So any program running even in user mode can use this instruction int num to raise a particular interrupt. Of course, if the program tries to raise an interrupt which cannot be raised in user mode, then that will be prevented. But then there are lots of interrupts which can be raised in user mode. Okay. So coming back to this point, so because before starting the interrupt service routine, the state of the current program needs to be saved. So what does this saving the state of a program mean? So essentially, if you think a program has a code, the source code, and at a particular point of time, it has some values which it needs to remember. So think of your C program. At any point of time, let's say okay, so your C program is running. Now suppose you are told that at a certain point of time, the program will be stopped and it will be resumed again later. What are the things that is needed to be remembered? B. If you have an answer, that's right. So your C program is running at a certain point of time. For some reason, the program needs to be stopped such that it can be resumed from that point again later. So what are the things which need to be remembered? Okay, Aryan says, right? Value of the registers, that means values of the different variables, and the stack pointer. Okay, anything else? Maybe the instruction at which, yeah, program counter, exactly what Rajat said. Maybe that also might be necessary, that at which instruction the program was. So if this much is remembered, then understand that the program can be resumed from that state. The code is of course there. The code is there saved, right? Apart from that, if the values of registers, the stack pointer, the program counter, if these values are remembered, then the program can be resumed exactly from that state. Right, so this is as if pausing a program, right? Just like we can pause a video and then we can resume the video from exactly from that point. Similarly, to pause a program, I mean, it might seem strange that we are pausing a program, but it's quite commonplace that to pause a program, you need to remember these things. So if someone, let's say the kernel, keeps a copy of these things of your program, it can later resume the program. When resuming the program, it simply has to read the register contents back from the memory to the CPU, those registers, and then it can replace read the value of saved value of the program counter into program counter, and then the next instruction will be executed, the next instruction of your program. Right, so this is what we mean when we say this line. The register state of the program is saved by the kernel. Okay, so basically this is how an interrupt is serviced. If an interrupt occurs, which may be a hardware interrupt or software interrupt, usually an interrupt is associated with a number, and that number helps the kernel to figure out which code to run next. So which code will service this interrupt. We use its IDT, a table called IDT, and yeah, so if an interrupt occurs, the context of the current program is saved, and the IDT is used to run the interrupt service routine, and then again the program is resumed. Okay, so that was our discussion on interrupts, which was needed because earlier days system calls used to be handled like interrupts. So let's proceed. If you have any question, feel free to ask. Sorry, originally system calls used to be issued using the same int instruction. Again, the system call handler routine was just an interrupt handler. And like interrupts, system calls used to be arranged in a table. So whenever a system call came, the program selects which system call it wants. So as I said, every interrupt, every system call has a number. So the program selects which syscall it wants by placing an index in a particular register. So let's say interrupt number 37, program wants to raise interrupt or syscall number 37. So there is a specific mechanism by which it will inform the kernel which syscall it wants. So this 37, let's say, will be placed in a particular register. And then this int instruction would be raised. And of course, if that system call requires some other arguments, then those arguments have to go in other registers as per convention. Can you think of any, just from what you have done throughout your BTech, can you think of any argument which might be required when doing a system call? All of you have done it. So when asking for a system call or when raising a system call, what kind of arguments may be needed? Exactly what Nisarg said. Let's say you are trying to take input. So you have to raise a system call and you have to tell that and which address should the input be stored. Right. So that is one argument which you need to inform before, I mean, if you want to raise this interrupt. Right, yeah. So even in printf, so from which address that data should be printed. Right. So these things have to be given as arguments while raising a system call. Similarly, there is a return value also. I think you know printf scanf actually returns something. If you don't, you look up the man, but printf scanf and these things also return something, which usually you will tell you whether operation has been successful, etc., etc. So again, this return value, the kernel will place it in some register and so on. Okay, so basically in the earlier days, the kernel leveraged interrupts to handle system calls. However, this mechanism is slow. So today, processors are totally pipelined. I'm sure you have read a lot about pipeline in your core course. And you know that pipeline stalls are very expensive. Now, cache misses can cause pipeline stalls. So the problem is that the IDT is in memory. The interrupt descriptor table, which we discussed, that is in memory. And all parts of that IDT may not be in the cache. So maybe an interrupt is raised or a system call is made whose that corresponding index of the IDT is not in cache. So there will be a cache miss. And this can make things expensive. So for example, it was empirically seen that system calls started taking almost twice as long from P3 to P4. So this Pentium series of processors. So till P3 things were fine, but when P4 came, and I would imagine that a lot more interrupts, lot more system calls maybe started to be given, etc. So then system calls started taking a lot of time. So then people thought of a new design. Before going to that, can anyone guess what can be a... So you understand the problem. The IDT is in memory. It may not be in cache, and therefore That can be a cache miss. So we will discuss what was done, but before that, can anyone guess what could be a potential way out? Okay, let's proceed. I think the answer will come up. So basically, the IDT entry is important to understand what is the next instruction to run, or what is the starting address of the interrupt service routine. So till now we were telling that we stored this in the IDT entry, which is in the memory. Instead of that, why not we cache the IDT entry for a system call in a special CPU register, so that you don't have to go to the memory or cache in order to get the IDT entry. It is a register. It is in a register. Right? So things seem simple, but then there is a cost. Now can you say what is the cost? Can anyone say? This should be an easier question. Okay, Nisarg is saying the number of system calls available. That is another way of telling it. So Nisarg, exactly. So okay, the Nisarg has now told the other way of also. So basically now you need many more registers. So either way, you have to say that okay, I only have this many registers, therefore only this many system calls are possible. Or if you want to give all the system calls that you used to give earlier, that means you will have to have more registers in the processor. Okay. So that is the cost. So basically the cost, I mean the transistor budget is increasing. You are thinking of now putting in a lot more registers. Is it worth it? Completely depends on how frequent system calls are. By the way, let me just have a 2-minute digression here. So you are now studying systems courses like operating systems, networks. Often you will find such questions come up, or trade-offs, where if you spend more, you can get a better solution. Question is it worthwhile to spend more? Right. So suppose till now you had a bike. You are now wondering whether you should go for a car. Maybe you have the money, okay, but then still, whether you should spend that money on a car? So then we start thinking about the utility. If I spend that extra money on the car, will it really help me? What else will I save? How much time will I save? How frequently will I save this time, and so on? So exactly those kind of questions. Having more registers in the CPU will of course make things fast. The whole IDT can be now stored in the registers. But is it worth it? So the question to be answered is, are system calls so frequent that we should not go to the memory every time to get the IDT entry? Rather, we should increase the number of registers. So that is the question, that is the decision we need to make. So yeah, typically it is nowadays the case that system calls are very, very frequent. So yeah, I mean, that is what has been observed. So now in the new architectures, there is a specific machine instruction which is used to raise a syscall or to issue a syscall. So essentially this instruction is, you might think it is meant for a program or a user program asking the processor to perform a task. And this instruction is hardware specific. Different architectures may have different names for it. This is called trap, SVC, etc. For x86 64 architectures, this instruction is called syscall. So the syscall instruction takes operands. Let's say syscall 10. So basically this is an integer number which says which system call the program wants. Now the instruction uses machine specific registers that store the syscall entry points into kernel code for every syscall. Right? So if a program raises syscall 10, it is predefined that which register will contain the syscall entry point. That means the starting point of that kernel code, which will which will do the work for the system call, or which will address the system call. So that what we were discussing as IDT 10 minutes back, the same thing, it's now the registers itself. So some register itself contains the syscall entry point into kernel code. So the starting point of that code which should be executed to leverage this, address the system call. And as usual, return values, arguments, etc., they go in other registers as per convention. Okay. So this is how nowadays syscalls are used. So in earlier days, syscalls used to be used the same way as interrupts, but that had this problem about the IDT being in the table, being in the memory, the IDT table being in the memory. So nowadays, people have shifted. So syscalls actually occur very, very frequently, and therefore people have brought instead of relying on a table in the memory, people have started relying on the registers itself. Okay, so now so that was a bit of a lower level discussion about interrupts and syscalls. But now let us discuss at a bit higher level that when you are writing a program, how will you make system calls? Will you use an int instruction or a syscall instruction? Maybe not. So let's see, because again, the OS is giving us nice abstractions so that we can make system calls easily. So we don't have to remember exactly which system call number is meant for taking input. Right? So this is the kernel is giving us easier abstractions. So let's discuss that. So when we are writing programs in a high-level language like C, we can think of syscalls in a higher level context. That is because the kernel is providing an interface to the services made available by it. Right? And these services actually execute hundreds of thousands times every second. Because remember, it's not only about your program. There are actually hundreds of programs running. Right? And all the different programs are making different types of system calls. Even hardware parts like the timer are making, let's say, raising interrupts or doing things like them. So therefore, the services that we are going to talk about, they are actually being used hundreds or thousands of times every second. So user application programs need not be worried about that level of detail. Rather, while writing a program, we can use an application programming interface or API. So the API will basically be a set of functions. You can think of them as a set of function calls. We will discuss some of the functions, but you see some of the names here: fork, pipe, exec VP, and so on. Now, these APIs or these functions are also loosely termed as system calls. So though we have discussed the lower level that system call is a machine instruction, etc. Since we are not directly using those machine instructions, for our purpose while writing a program, we will use these application programming interfaces, basically function calls. So loosely, these function calls or APIs are also called system calls. So here is an example. Think from our C programming knowledge, we all are aware of fopen, fgetS, printf, fclose, etc. fprintf. Now these are C library functions. fopen, fgetS, fprintf, fclose. These are C library functions. Corresponding to them, the Linux kernel gives us system calls like open, read, write, close. Purposes are the same. So open is actually used for opening a file descriptor. That what we do as fopen. So fopen internally calls open. So open is a system call, whereas fopen is a C library function. So in this picture, you see we are demonstrating a particular system call called read. The purpose is read from a file descriptor. By the way, what you are seeing here is a snapshot from the man page. Man is the manual included in any Linux distribution. So we hope that you are used to see man pages. If not, please develop the habit, because man pages are possibly the most comprehensive source of information about a system call or even a library function. Right? So anyone here who habitually referred to man pages? Okay, but yeah, it is better to develop the habit of looking up man pages. Some of the man pages may not be very easy to understand. You need experience and all. But again, the man pages are the most comprehensive source of information about system calls and library functions. Therefore, at least some parts of the man page you should develop a habit of going through. Okay, coming back. So this is a snapshot from the man page of read. So read is a system call. Purpose is read from a file descriptor. And you see here the man page tells you how to use it. Hash include unistd.h. It's a file. And then this is the function prototype. So read takes as arguments an integer file descriptor, a void pointer buffer, a size t count, and it returns also as size t. So just intuitively, what do you think these purpose of these arguments? Intuitively? So fd, buff, count. Okay, yes, Ashutosh has given, and Nisarg also. So Nisarg and Ashutosh, they have given the answer, right? Good. So fd is the file descriptor from which data will be read. And how many bytes to read? That is count. And where will the data that is read be stored? That is void pointer buff. So buff is a memory address where the red data will be stored. Okay. So this is just one example of a system call, which is meant for input, that is reading from a file descriptor. Right. So yeah, so that is what we have discussed, that what are these function parameters for read. So this is the workflow of a system call. So when we write a program, we usually do we usually call library functions like say printf or scanf. Internally, those printf, scanf, they make lower level standard C library calls like read and write. And for our purposes, we often refer to these read and write as system calls. But even lower down, all these use a syscall instruction with specific numbers to actually, execute a machine instruction of syscall. Okay, please keep yourself muted. It seems someone is unmuted. Okay, so for our purposes, we will possibly discuss at this level, this read write. For our purposes, these are system calls. But as we have discussed in the earlier part today, internally there's a machine instruction which helps these functions to make a system call. Okay, now there are lots of system calls. We will just tell you a couple of names, but again, we expect you to read these or know these system calls. There are lots of information on the web, as well as the man pages are the most comprehensive source of information. So let's see. So, okay, all of these will not make sense right now, but as we go ahead in the course, most of these will start making sense. So there are a large number of system calls for process control, like fork, exit, wait. So like you can create a new process using fork. What is a process? We will just come to that next class. The next topic is on processes. So you can create a process, terminate a process. For these, there are system calls. Some of these should be familiar, like say allocate and free memory. So you already use malloc, calloc, free. So there are system calls for allocating and freeing memory. Right. So, okay. Now, there are other system calls for file management. This should be more familiar, like create file, delete file, open and close a file, etc. Similarly, there are system calls for device management. Next, this is an important topic which we will spend a lot of time on, inter-process communication. So, sometimes one program needs to talk to another. Right. So I think, in a previous class, one of you asked that. So suppose, as I said, like say two programs are running, A and B. Now we cannot directly say that when A will be executed and when B will be executed. That depends upon the kernel or the scheduler. However, let's say we have written two programs where A takes an input, program A, and program B operates on the input. So unless the input is taken, B cannot operate on the input. So that means we have written say two programs, one of which takes an input and passes it to the second program B, and then B does something on the input. So here different kinds of inter-process communication is needed. First of all, A needs to share a data with B. Also, some synchronization is needed. Like first A should take the input and then B should work on the input. Right, so these kind of functions come under the purview of inter-process communications. Right. So just intuitively you see this shared memory. Okay. So again, we will go into details, lot more details in the course, but just for now, the intuition is that your program till now, whatever programs you have written, they are kind of standalone. the program used by your, the memory used by your program only belongs to your program. But in this course, you will learn how to write multiple programs which share some memory. So as I said, let's say program A takes some input and passes it to B. One way of doing it is that you have some shared memory between the programs A and B. So A takes the input and writes that in that shared memory, from where B can also access it. Okay. Okay, so Professor Mainak has given some questions which think about it. We are not answering them right now. So why do we need the read system call and not directly one system call for fgetS, one for scanf, etc.? So also, what does an API of a system call mean? So these are more involved questions where, I mean, so this question is, so the question being asked by Moinak, I'll hand over to him right now, that these are not from the perspective of using the system calls, but think about those who have designed the system calls. Why did they not design one system call for fgetS, one for scanf, etc.? Why did they give a read system call? Anyway, coming back. So yeah, so there are a lot of such system calls. This set of slides gives a list, but maybe, yeah, so feel free to look at these resources which are here. So you won't understand possibly all the system calls right now, but as we go ahead in the course, some of the system calls and their purposes will become clear. Okay, so Mainak, if you want to add anything, please do so.
Yes. So I just wanted you to think, simply because that now you know, sorry, now you know what a system call is, and that is something that you are using from your first year or even before, if you're coding before that, right? I mean, you are using at least reading and scanning, creating menus and all this, and everything uses system calls, as we discussed yesterday and today. Now, from a developer's point of view, because there's a WES introductory course for designing operating system, why do we need this weird sounding read, open, close, or actually simpler sounding system calls? And why then are we not using them directly, rather than using fgetS, scanf, printf, and these functions? So this actually is a question which you can Google. I'll just give you a hint. Operating system code is static, and once you write it, you have to ship it to everyone, perhaps millions to tens of millions of computers, and they have different use cases. That is the hint. So you need to actually create, as a developer, you need to create some calls which are applicable in those very different scenarios. But think about that. Based on that idea, why do they come up with this read, write, close, all the system calls? And if you can find an answer, write it on MS Teams. This is again not for particularly for exam. Whatever Professor SG has taught and we're discussing now, it will be an exam. However, this question is a bit advanced and force you to think about how you would either build or improve operating system as a developer. So write your answer in MS Teams if you're interested in a little bit advanced thing, not for exam, but whoever is interested.
So thanks, Mainak. So any question from anyone? Okay, if not, then thanks everyone. So let's end this class today. By the way, we are making the slides available. So if you see on your Teams, there is a files. There is a tab called files. Under that, you will find the class resources, which are these slides. We are putting up the slides there. Also, the recordings of the lectures are also available there. So I hope you know this. So we are putting up slides under files. Okay, then. Thanks, everyone. We will continue next week.